The first experiments to get computers or computer programs to simulate human problem solving actually started around in the early 1950s. I'd even say just before computers became available to the general public. For example, there was a early computer at Princeton designed by John von Neumann. Several copies of it were built. He was a mathematician who appears to be the first or second person who clearly had the idea of the modern computer. There was also a fellow in Germany named Konrad Zuse who worked out this idea, but he couldn't get anyone to pay attention to him. And the main idea about the main difference between the modern computer and the computing machines that had come before is that the old computing machines could perform the same kinds of operations. They could add numbers, they could store things here and there and get them out again. But what they did was determined by a fixed program, usually by a set of punched cards, which would say first do this, then do that, then do that. Maybe if this happens, use this deck of cards. If that happens, use a different deck. So that was the early computers. And what von Neumann and Zuse realized is that wouldn't it be better if you stored the program in the computer's memory just like the data, and then you could have, they were thinking of the future rather than the present, and then maybe someday the computer could compute a new program for a new job and store it, and that made the computers more powerful. And in the early 1950s, for the first time, computers got enough memory so that there was actually room to store new programs in them, and some pioneers started in 1954, 5, 6, started experiments where they actually wrote programs that wrote new programs that would then run. And this led to the development of certain languages which were very good at writing, in which you could write programs that would write in the same language so they could keep changing. There was a lot of progress, and by 1960 we had two major languages which were good at modifying themselves. Unfortunately, these languages were a little bit unfamiliar to other people who didn't see the great power of programs that could change themselves, and the world was overtaken by other terrible languages like the famous C language, or Fortran, or Algol, and so forth, which became universally popular, and in which it's almost impossible to write programs that change themselves. That's just a parenthesis. There's, is it Bentham's law that says the bad drives out the good? Whose law is it? Gresham's law. In modern software practice, we see this. I can't understand why this 35-year-old language called Unix has suddenly become popular, but the only thing I can think of is that the other operating systems got filled with so much garbage in the intervening 35 years that nobody could deal with them. And it's not that Unix is the latest thing. It's the last fossil that hasn't completely dissolved from the past. So they're starting over, and as far as I can see, they're starting over to make the same mistakes. Well, in the early days of this thing called artificial intelligence, we started to try to make programs that would do very advanced things. Maybe that was a mistake. One of the first programs that I was involved with was a program that would prove theorems in Euclidean geometry. It just crossed my mind. I'm curious how many children learn Euclidean geometry anymore. What Euclidean geometry used to be was a rather amazing subject where you would learn a dozen assumptions, like that 2 points determine a unique line, or if there are 2 lines, then they're either parallel and don't intersect, or if they intersect, they just intersect in one place, and that two triangles are the same in all respects if they're the same in two sides and an angle between them, and so forth. Euclid, I don't know when the hell Euclid was, probably 600 BC. This was a wonderful subject because you were in a world where assumptions were very simple and there were only a small number of them, and you used a logic which was very clear, and so it's a beautiful thing, and you get all sorts of interesting truths and falsehoods, and you can check them and so forth. For some reason, a large fraction of humans find it very hard to deal with a subject where you don't have to know much. It's a great mystery to me how you can be bad at mathematics when mathematics is the simplest of all things. Yet you get people who get high grades in history or social sciences where nobody has the slightest idea of what's going on, and you can't understand anything. That's a side subject. How could a person be bad at mathematics? It must be that somehow they get a wrong model of what the activity is. I remember once trying to tutor a student who couldn't prove theorems, and I said, "What's your trouble?" And he said, "Well, I think I was sick the day that the teacher explained how you prove theorems." So this poor kid thought that there was some special way to do this. Of course, the way you do it is by using general common sense knowledge of figure out if two things are related, which one is causing the other, and that sort of thing. And in fact, when I told the student that there wasn't any known way to do this yet, he brightened up and got better at it, because he really seemed to think there was something he didn't know that he needed to know, and that it wasn't a matter of drawing on the general resourcefulness that you'd expect every normal person to have. If you didn't know you're supposed to be a little bit original, maybe it's hard. Anyway, I was fussing with geometry a little bit, and I wrote down a draft for how would you make a program that would in fact take some statement in Euclidean geometry and find a proof for it. And that was in the late 50s. And by 1960, a little group at IBM Research managed to write one of these programs that in fact was pretty good and could compare pretty well to a high school student's ability at that sort of thing. Shortly after that, we had a student who wrote a program that solved symbolic problems in calculus, integral calculus, and it did it well enough on an old computer that it could get an A in the MIT first-year calculus course. Of course, it couldn't do the word problems, but it did quite well in calculus, and we told it about 50 or 100 little rules of thumb that you use in different situations, and worked very well. So here we're aiming at what's considered to be fairly high quality of human performance. Before long, in fact, that program had evolved into a computer that was better, into a program that was better than any human in the world. And there was a commercial version of that program called Maxima, for Project Max Symbolic Mathematician Program, which in fact put a lot of mathematicians out of business who had been involved in trying to find new ways to integrate functions. It's an exciting story. But it couldn't do word problems, so a couple of years later, one of our graduate students decided he would try to get a computer to solve less formal problems, like John was 4 years older than Joseph when Joseph was twice as old as John had been 10 years ago. Most high school students, I don't know if that's a real problem, but most high,
pi years old.
Right. But most, even high school students have considerable trouble with that. If you can get your head clear, which is hard, you end up with two equations about John's age and the other guy's age, and the two equations are different, and if you're lucky, they have a unique solution. And this program was able to take pretty complicated English sentences and figure out what equations they were talking about and solve the equation. If it was about anything else, it couldn't do anything, and we tried to improve that program for a while, but it was a dead end in the sense that if you asked the program to do anything else, it didn't know what the words mean. So people started to use computers for other specialized problems, and by 1980, we had tens of thousands of programs, each of which was quite good at doing some very special thing. But there was no program that could do the kinds of things that you'd expect your 5-year-old to do. In fact, 5-year-old can beat you in an argument if you're wrong enough and the kid is right enough. To make a long story short, we've regressed from calculus and geometry and high school algebra and so forth, and we're trying to get people to work on common sense problems like the sort that every 4 or 5-year-old can do. And what's interesting is that although there are perhaps 100,000 people writing expert programs, maybe even 1 million around the world, expert specialized programs, I've only been able to find about a dozen people so far in the world who are interested in trying to do simple, everyday, common sense jobs of the sort that all children can do.
Thank you.